Welcome back to my channel, everybody, and welcome back to another video in this computer organization course. So today we will be focusing on chapter 2 homework part 1. So what we've gone through so far is we're going to go over the conversions from decimal to binary or binary to decimal. We're also going to look at hexadecimal conversions as well. And then we're going to go over the ones complement, twos complement, and sign magnitude. So we have a lot to do, so let's get started. Alright guys, so our first question is asking us to pretty much do a decimal to binary conversion. So we want to convert the decimal number 25,84375 into binary form with a maximum of 6 places to the right of the binary point. So how do we do this conversion? If you don't know, please check the link in the description and I'll leave an info card for you guys to check that out. So what we're going to do is we're going to separate the integer part and the fractional part. And we're going to do these separately. So we're going to figure out what powers of 2 go into 25 perfectly, which is 16 plus 8 plus 1. So that's 2 to the 4, 2 to the 3, and 2 to the 0. Let's do 5 places. 1, 2, 3, 4, and 5. 2 to the 0, 2 to the 3, and 2 to the 4. And we're done with this part right here. So we'll save that for now. And what do we do over here? Here we want to do a multiplication of 2, a repeated multiplication of 2 to figure out our place. So what we're going to do is 0.84375, and we want to multiply that by 2 and keep its binary digit. So what do I mean by binary digit? So this answer will be 1.6875. We want to keep this value right here, and we want to multiply this again. So it'll be 0.6875 times 2. And that value will be 1.375. And we're going to do the same thing. 0.375 times 2 equals 0.75. Keep this as well. Do the same thing over and over. 1.5, 0.5 times 2 equals 1.0. And we are left with 0. And the way we do this is we read down. Alright, and now we want to combine our values. So we're going to combine the integer part, which is 1, 1, 0, 0, 1. And now we want to combine our fractional part, which we're going to read down. So it's 1, 1, 0, 1, 1, 0. So this is 25.84375 in base 2. So we're moving on to question 2, which is pretty much just asking us to convert a hexadecimal number, AC12, to binary. So how do we do that? So the way we do this, the way we convert from hexadecimal to binary, is we use 4 places for every single letter. Every single letter corresponds to 4 bit places. And why is it 4 bit places? Because the radix of hexadecimal is 16. So the values that can actually occur in the hexadecimal numbering system is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. So A corresponds to 10 all the way down to F equals 15. So what we want to do, and by the way, the radix of 16, what is that in powers of 2? It's 2 to the 4. That's why we use 4 bits for every single value here. So we want to split this up. So A, C, 1, and 2. 4 bits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. And let's separate these. Alright, so remember each place begins at 2 to the 0, going left to 2 to the 3. Everything's the same, pretty much. Alright, so let's get started. A, it corresponds to the value of 10, correct? Right here. A corresponds to the value of 10. So what we're trying to figure out is we want to figure out how to get these binary numbers to equal 10. So we want to do 8. It's the highest power of 2 that goes into 10 without going over. And then we are left with 2, right? So think about it as 10 minus 8 equals 2. 4 does not go into there, but 2 to the 1 does. Alright? So 8 plus 2 equals 10. Now for C. C corresponds to 12. So this value is 12. So what we want to do here is we want to find the powers of 2 that equal 12. So the first one would be 8 and 4. So 8 plus 4 equals 12. We don't need any other numbers. What about 1? 1 is the easiest pretty much. It's just the last place. Have everything else 0. And what about 2? This place right here, which is 2 to the 1. 2 to the 1 equals 2. And this place right here is 2 to the 0. 2 to the 0 equals 1. So, A, C, 12, and base 16 equals. And we read this way. We're going to read all that way. 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And that is the answer in base 2. So moving on to question 3. So question 3 pretty much asks us to represent the following decimal numbers using an 8-bit register. So we want to show them in sign magnitude, 1's complement, and 2's complement. So we're going to first work with 60, and then we're going to move on to negative 60. So let's figure out what 60 is as an unsigned integer. So 60 corresponds to 32 plus 16 plus 8 plus 4. Correct? So that's 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2. So unsigned, we're going to use an 8-bit register. 1, 2, 3, 4, 5, 6, 7, and 8. So 2 to the 2, 3, 4, 5. 2 to the 5. 1, 1, 1, 1. Everything else is zeros. So this is what it is. This is what plus 60 is in unsigned. So what about in sign magnitude? It's going to be exactly the same, because in sign magnitude all you care about is the sign bit, and positive is corresponding to the sign bit. What about in 1's complement? And this is where it gets a little tricky, because you don't change anything whatsoever. You think, the question makes you think that you need to change something out, but you don't. 1's complement, sign magnitude, and 2's complement representations are all different ways to represent negative numbers, but positive numbers will be exactly the same in every single form. So two's complement will be exactly the same. Two's complement will be exactly the same. So 60 plus 60 is the same in unsigned, signed, one's complement, and two's complement. They're all the same. So now we get to negative 60. This is where it differs. Alright, so let's figure out plus 60. Remember, we want to figure out plus 60 first and then use the different negative representations. So we want to figure out 60 and then use sign magnitude, then one's complement, then two's complement. So let's figure this out. So it's going to be same thing as before. 1, 1, 1, 1, 0, 0, 0, 0. Alright, so let's figure out the sign magnitude. And here's a hint. Sign bit is 1. So how do we change this from plus 60 to negative 60 in sign magnitude? So what we're going to do is we're going to add a sign bit, which corresponds to a 1 in negative, and everything else is the same. So this is negative 60 in sign magnitude. The only thing we changed is this 1, which corresponds to a negative value. All these values are constitute into the sum. This does not add any value. It's not like it's like the 2 to the 7th place. No, this just adds negative. Mm-hmm. Now let's do one's complement here. One's complement is a little different, but remember what I said? You always want to change from the positive binary number. So in one's complement, what we're going to do is we're going to invert all zeros to ones and ones to zeros. So what we're going to do is we're going to invert all the zeros to ones and all the ones to zeros. And there you go, negative 60 in ones complement. That is negative 60 in one's complement. Alright, so plus 60, let's rewrite that again. And how do we do two's complement? Two's complement, keep least significant 1, 1. Invert everything to the left. So what do I mean by that? So you're going to find the least significant one, and you're going to keep this 1 and invert everything to the left. Everything to the right you're going to keep. So we can just bring these 3 down. They're going to stay the same. Remember, the least significant 1 stays 1. Everything else gets inverted. 0, 0, 0, 1, 1. So everything to the left, all the zeros become 1, and all the 1s become zeros. And for the last question of the video, we're going to figure out the decimal value of an 8-bit binary number, 100111110, and we're going to figure them out, what the values are in unsigned number, sign magnitude, one's complement, and two's complement. So let's just get started. So for A, unsigned number. So there is no sign bit, So the leftmost bit has a value. All right. So what do I mean by that? 1, 0, 0, 1, 1, 1, 1, 0. So this leftmost bit, when we do sign magnitude, 1's complement and 2's complement, this pretty much corresponds to negative. But in unsigned numbers, this actually has a value. So this is a 2 to the 7th place. And then we have 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. And this is neither positive nor negative. It's just unsigned. So what we're looking at is 2 to the 7 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 1, 128 plus 16 plus 8 plus 4 and plus 2. We are looking at 158. 158 for that value. Alright, let's just erase everything. Alright, now we're going to move on to sign magnitude. So 1, 0, 0, 1, 1, 1, 1, 0. So in sign magnitude, we do have a sign bit, which is the leftmost bit. So this right here is our sign bit, and 1 corresponds to negative. And this has no value. It doesn't add a value to it. It just determines if this binary number is positive or negative. So the places that do add value is the 2 to the 1 place, 2 to the 2, 2 to the 3, and 2 to the 4. So in sign magnitude, what we're looking at is negative 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 1. So what we're looking at is negative 16 plus 8 plus 4 plus 2, which is negative 30. Alright. Move on to the next one. So for the first one, it was 158. For this one, it's negative 30. Now we're going to figure out 1's complement. So what we want to do, we want to write out our binary number. And we want to change this. First step, change sign bit to 0. Since we want to convert from a positive number. Convert from a positive number. From a positive number. So what we're going to do is we're going to change this back to 0. Because remember, 0 corresponds to positive. Alright, and the second step, invert all numbers. So what we're going to do is we're going to change the 0s to 1s and the 1s to 0s. There we are. So remember, this is a sign bit right here. It adds no value. So what we're looking at right here is 2 to 0, 1, 2, 3, 4, 2 to the 5, and 2 to the 6. 2 to the 6 plus 2 to the 5 plus 2 to the 0. which is 64 plus 32 plus 1, which is negative 97. So 158, negative 30, negative 97. And in 2's complement, we'll do the same exact thing. For the first step, we're going to convert this into a positive number. And we keep this the same. Now we want to use 2's complement. So how do we use 2's complement? We find the least significant one. We're going to keep this one and invert everything to the left. So we keep this right here. We drop that down, 0, 1, and now we invert everything to the left of this. So it's 0, 0, 0, 1, 1, and 1. So this is our sign bit, negative, 2 to the 6, 2 to the 5, and 2 to the 1. So that's 64 plus 32 plus 2. And what we're looking at is negative 98. Well, thank you guys for watching this video. If you did like the video, please leave a like, comment, and subscribe for some more educational content.